welcome if you've joined us after watching the main lesson modelling and you've come for a bit more with extension, or welcome if you've just come to extension. I'm having a go at live modelling with a bit of a time pressure, so it's not perfect, but hopefully it will be on in time for it to help you before the 17th of June deadline. Go at the extension question. So this first one is very similar to the question that was the last practice in the main part of the lesson. We're being asked to calculate the temperature change, so that is our delta Q part. We're being told we've got this much energy being transferred, that's our delta Q, and we are transferring to a standard unit of kilograms, a smaller mass of water. Now, we will have to remember and look up from the other parts of the lesson that the specific heat capacity for water is 4,182 joules per kilogram degrees Celsius. I'm sure I've remembered that right. I'm just going to look and check I've got that right. Oh, look at that. The brain hasn't gone completely soggy yet. So, in this case, I'm going to substitute in first. I'm going to do it the way I prefer that I was just talking about a moment ago. So I know that I've got 8,000 joules, that is equal to a mass of 0.2 times by the specific heat capacity times by a change of temperature that I'm trying to find. Then I'm going to solve this bit, and definitely using a calculator for that. There we go. Now I'm down to 3 parts, so if I want the security of my triangle, I know that if I cover over the 8,000, I need to have these in the bottom and 8,000 in the top. Okay. So now if I cover over the thing I'm trying to find, the change of temperature would be 8,000 divided by 836.4, which gives me 9.56, which I bet, for neatness, I probably rounded up on your answer document, didn't I? I hope I've got the same answer as I put on your answer document at this point, because I believe that would be a change of temperature, which makes sense for that mass of water, of 9.6 degrees Celsius. Okay, on to the next example. So now we have a kettle that is filled with half a litre of water. Now that's a red herring, because we don't care about the volume of water at all in this equation. But we do care about the fact that it's got a mass, and that mass has been given to us as 0.5 kilograms, standard units again. Oh, formatting, sorry. I can see it is screaming at me. The temperature of the water is 10 degrees. Now that's suggesting to me it starts at 10 degrees. How much energy is going to be needed? So it's asking us about the delta Q part of this question. How much is needed to bring the water to boiling point? Well, boiling point for water, assuming it's pure water here, would be 100 degrees Celsius. So we're trying to go from 10 to 100. In other words, a change of temperature of 90 degrees Celsius. And then, oh, this is a really tricky question. I was mean putting this one in, wasn't I? And then you are going to change the state of that water. So this is a 2 equation question, because this one also involves us finding out the latent heat, so the specific latent heat as well. So we'll come to that bit in a minute. Right, we have got delta Q. The thing we're trying to find out will be the mass, which is a half, times by the specific heat capacity of water, which I reminded you a little while ago, but I should remind you again, is 4,182 joules per kilogram degrees Celsius. And we need to times that by the 90 degrees that we worked out, don't we? So calculator at the ready, times in those numbers together, we get 188,190 joules. That is how much energy has been transferred to change the temperature of the water from 10 degrees to boiling point. But then the water is going to change state. So we need the other equation, and sorry, I haven't copy and pasted it in here ready. The other equation that we need to use is the one that you practiced in the first part of this lesson. So the specific latent heat, the energy required to change state in joules, is equal to the mass of the substance you're changing state times by its specific latent heat. So here we have got to find out how much energy is needed to bring the water to boiling point, and then, so we've got this much energy already, how much extra energy are we going to have to add on to that to find the total? That's what it means. So the energy can be found by the mass, 0.5, times the specific latent heat of water. Now that is the specific latent heat of water when it's evaporating. So I am going to admit that I am now looking that up. Let's just make sure. Right, it's 2257, but that is kilojoules per kilogram. So I need to put that into joules per kilogram. So I need to times that by 1,000, which means I effectively need 3 more zeros on the end. There we go. So to work out the energy that I need to evaporate all the water in the kettle, I need to work out the energy required to change the state of 0.5 kilograms of water when water has a specific latent heat of 2,257 kilojoules per kilogram. So I've had to times that by the 1,000 to get it into joules per kilogram there, to keep everything in the same standard units. When I do that on the calculator, I get 1128500 joules. And then the total energy in this question will be what I got in the first part and the energy needed to change the state in the second part. So that means the total amount of energy comes to... Oh, I wish I had a little drum roll app right now. Probably could add that on, couldn't I? There we go. That's a bit untidy, isn't it? I might divide it by 1,000. 131 and round it up. 7 kilojoules. That looks a bit neater, doesn't it? 1,317 kilojoules of energy in total to take half a kilogram of water that's at 10 degrees, heat it all the way up to its boiling point, and then evaporate it all away, turning it all from a liquid into a gas. I hope that wasn't too waffly. You'll have to let me know if it was, and I'll try and do that one again.